In the section on aeronautical charts, we looked at symbols on the Cincinnati sectional. We covered an area from Claremont County Airport to Fayette County Airport, over to Richmond, Indiana Airport, and back to Claremont County Airport. Now, let's look at the navigation planning that's done on the ground for the same trip. This planning is one of the key elements of proper pre-flight preparation. We'll use pilotage, dead reckoning, and radio navigation on our trip.
The only thing pilotage involves is looking out the airplane window and flying along the course by reference to pre-selected landmarks until reaching the destination. Deduced, or dead reckoning, is calculating the effect of the wind and speed on the airplane, so a compass heading, ground speed, time en route, and fuel required can be estimated. To radio navigate, an instrument indication helps lead the pilot along the desired course. Using a plotter, which is a device for measuring distance and direction, determine the distance from Claremont County Airport to Fayette County Airport along the course line. Some plotters have a sectional scale on one side and a World Aeronautical Chart scale on the other, so take care to use the correct side. Simply read off the nautical mile scale that it's 47 nautical miles. From Fayette County Airport to Richmond Airport measures 66 nautical miles. From Richmond Airport to Claremont County Airport is 50 nautical miles. The total mileage for the trip is 163 nautical miles. The next step is to determine the direction to each airport for our trip.
In the charts section, we showed how meridians of longitude run north and south and meet at the poles. By using these same meridians, direction from one point to another can be determined in degrees, measured clockwise from true north. A course measured this way is called a true course.
To determine the true course from Claremont County Airport to Fayette County Airport, lay the plotter on the course line drawn on the chart between the airports, with the center of the protractor on a meridian. Measure the angle this line makes with a meridian. Because the course is in an easterly direction, read the angle on the outer scale. In this case, the true course is 51 degrees. From Fayette County Airport to Richmond Airport is a westerly direction, so we use the inner scale. The true course measures 280 degrees. From Richmond Airport to Claremont County, the true course is 145 degrees. If a course line is long and crosses numerous meridians, measure the course on one of the meridians closest to the center of the course, since meridians converge toward the poles.
Now that we have distance and true course, we must consider the wind direction, since it affects our heading. Wind information received over the radio for takeoffs or landings is given as a magnetic direction. This is done to eliminate confusion between true and magnetic winds, since runway headings are also magnetic. All other wind information, spoken or printed, is given as a true direction.
While flying from point A to point B, if there is no correction in heading for wind not aligned with the course, the airplane will drift off the intended track. The difference between heading and track is known as drift angle. To offset this unwanted drift, turn the airplane slightly into the direction of the wind. The direction in which the airplane's nose is pointing will be different from the true course. This is called a true heading. The combined effect of the movement of the airplane and the movement of the air results in the desired ground track. The angle formed between the heading and the course is called the wind correction angle. But there's more.
The speed of the wind also has to be considered. Think of wind as simply an ocean of air moving over the Earth's surface in a specific direction. True airspeed, the rate at which the airplane moves through the air, is not affected by the motion of the air. But the motion of the air does affect the airplane's ground speed.
If we're flying east in a Skyhawk at 110 knots true airspeed in calm air, the ground speed is going to match the true airspeed at 110 knots. If the air begins to move from the west to the east at 15 knots, the true airspeed remains the same, but the ground speed increases by 15 knots, from 110 to 125 knots, due to the tailwind. If we turn the airplane 180 degrees and head back west, the wind becomes a headwind. The true airspeed will not change, but the 15-knot headwind reduces the ground speed by 15 knots, from 110 knots to 95 knots. If a turn to the south is made and no correction for wind is applied, the airplane at the end of 1 hour will be 110 nautical miles south from where the turn was made, and 15 nautical miles to the east because of the movement of the air.
In these examples, the true airspeed remained constant at 110 knots, but the ground speed changed. That's because ground speed is a combination of the movement of the airplane with the movement of the air. Direction and speed of the wind are therefore of prime interest to a pilot.
Next, we have to consider the magnetic compass, which is the instrument used to set direction. It's a very reliable instrument, not dependent on any power source in the airplane to operate. It's also the instrument you referred to when setting the gyro-stabilized heading indicator.
However, when planning a trip, you have to take into consideration two factors which affect magnetic compass indications. These are magnetic variation and compass deviation. By definition, variation is the angle between true north and magnetic north at any given location.
The magnetic North Pole is actually located in Canada, more than 1,000 miles from the true North Pole. On sectional and world aeronautical charts, the amount and direction of variation, which change from time to time, are shown by means of broken magenta lines called isogonic lines. These connect points of equal variation. The line that connects points at which there is zero variation between true north and magnetic north is called the agonic line. What this means is that on the east coast, the magnetic compass needle will point to the west of true north. On the west coast, the needle will point to the east of true north. Roughly, on a line through the western Great Lakes into the Gulf of Mexico, true and magnetic north coincide. Since courses are measured on meridians pointing to true north, but flown using a magnetic compass that points to magnetic north, a method of converting from true to magnetic direction is used. This conversion is done by adding or subtracting variation, as shown by the nearest isogonic line on the chart. For the next illustrations, assume there is a no wind condition. To fly a true course of 51 degrees from Claremont County to Fayette County Airport, check the nearest isogonic line. It's 5 degrees west. This amount is added to 51 degrees to obtain a magnetic course of 56 degrees. Let's look at another example. Assume that we are in the Los Angeles area, where the variation is 14 degrees east. To fly a true north course of 360 degrees in this area, you must subtract 14 degrees and fly a magnetic course of 346 degrees. A good way to remember if you add or subtract variation is by using the verse, "East is least and west is best." The rule is true when you start from true. What this means is, if the variation is east, it's least, so you subtract. If it's west, it's best, so you add. This is valid as long as the conversion is from a true course to a magnetic course.
The other factor affecting magnetic compass indications is deviation. Deviation is the deflection of the magnetic compass from its normal reading caused by some magnetic influence in the airplane itself.
Every airplane must have a compass correction card. The card is filled out by the manufacturer when the airplane is new. It's revised by an authorized person whenever work is done on the airplane that may affect the compass, such as when new radios are installed. The compass card is usually mounted close to the compass and shows any addition or subtraction necessary to correct for various headings. The corrections are usually shown at 30-degree intervals. 60 degrees is closest to our course of 51 degrees, so we'll subtract 2 degrees from our magnetic heading to get our compass heading. A compass heading is the reading that's followed to achieve the desired course. A good way to remember the steps to determine compass heading is by using the verse, "TV makes dull children." What this means is that after measuring true course and applying the wind correction, a true heading can be determined. Next, apply variation to get the magnetic heading. Finally, correct for deviation, and you arrive at a compass heading. The best way to keep a record of all these calculations is by using a flight log. There's one included on most flight plan forms.
In addition to distance in calculating the compass heading, we also want to determine the estimated time en route, ground speed, and how much fuel will be required. All these calculations can be done using either pencil and paper or a flight computer, of which there are two types. There's the old mechanical E6B, which is just a circular slide rule. Also, there's an electronic type, which is quickly replacing the old E6Bs. For our flight planning, we'll use the electronic type because of its accuracy and ease of use.
We will also need the pilot's operating handbook for our specific airplane, since it's the only source of some additional information we need for our calculations. This calculator expresses all airspeed problems with temperature in Celsius, altitude in feet, speed in knots, and distance in nautical miles. These are the units most often used in aviation. The weather briefing forecasts winds at 3,000 feet to be from 340 degrees at 9 knots. The temperature is 5 degrees Celsius on the ground at Claremont County Airport. Therefore, using the standard lapse rate of 2 degrees C per 1,000 feet, we can estimate the temperature at 3,000 feet to be about 1 degree Celsius. On the trip, we'll plan to fly no higher than 3,000 feet. We'll navigate the first leg from Claremont County Airport to Fayette County Airport using dead reckoning and pilotage, and fly at an altitude of 3,000 feet. To calculate the dead reckoning information for this leg, we need first to determine true airspeed. Use the graphs or tables in the performance section of your pilot's operating handbook to do this. Select the cruise performance that best fits your needs. On the first leg, we will use a true airspeed of 115 knots. We'll double-check all the true airspeed figures once we're in the air. The next step is to select heading and ground speed. Press Enter and put in the wind direction of 340 degrees. Now, enter the wind speed at 9 knots and the true course of 51 degrees. Enter the true airspeed of 115 knots, and the answer for ground speed is 111.7 knots with a heading of 46.8 degrees. We'll round these to 112 knots and 47 degrees. The 47-degree heading is only corrected for the wind. We still have to add 5 degrees west variation, which we get off the sectional chart, and subtract 2 degrees for deviation from the compass correction card in the airplane. Our compass heading is 50 degrees. This is the direction we'll follow on the compass as we start our flight. Now, let's figure the time required to fly the first leg. Select Leg Time, press Enter, and follow the prompts. Flight time will be 25 minutes and 14 seconds. Figure it at 25 minutes. The next 2 legs will require 60 minutes of flight time, so the total flight time for all the legs is 1 hour and 25 minutes. Since we'll be landing at each airport, let's figure an additional 5 minutes will be needed for each leg to cover climb to altitude, descent, pattern, and taxi time. This raises the total time to 1 hour, 40 minutes. Remember also, federal aviation regulations require that day VFR flights must have enough fuel to fly to the first point of intended landing, and, assuming normal cruising speed, to fly after that for at least 30 minutes. To cover this fuel requirement, add 30 minutes to the 1 hour and 40 minutes trip time to get a total time of 2 hours and 10 minutes. Now, let's figure the total fuel required for the trip. Select Fuel Required and press Enter. As prompted, enter time required at 2 hours and 10 minutes and press Enter again. Find the fuel burn rate in the pilot's operating handbook. Enter the rate of 9 gallons an hour for the Skyhawk. The amount of fuel required for the trip, plus reserve, will be 19.5 gallons. Since the Skyhawk holds 53 usable gallons, having enough fuel presents no problem. Also, a check of the airport facility directory shows fuel is available at our destination airports if more is needed for any reason. Since we will be navigating the first leg using pilotage, let's select a few checkpoints. We will use the town of Owensville and the racetrack, since they are close to the Claremont County Airport. This will help us get started in the right direction. The next checkpoint will be the town of Midland, a road, and a railroad. This will put us about 20 nautical miles from Claremont County Airport. Next up will be Airborne Air Park on the left. Now we are 28 nautical miles from Claremont County Airport and have approximately 17 nautical miles left to go. Next, we should see the town of Sabina off to the left and the town of Washington Courthouse over the nose of the airplane. The chart shows the airport is just north or above the town, with a railroad track, road, and obstruction close by. On this and all trips, take note of the airports along the route in case a diversion to one is required. We'll also take along a St. Louis sectional in case we need or want to go farther west into Indiana. We're planning on landing at Fayette County Airport. A check of the airport facility directory shows one runway, 422. It's 5,100 feet long, 75 feet wide, and is paved with asphalt. The CTAF is Unicom on 122.8, and the field is attended from 1400 to 2300, Monday through Friday. 100-octane fuel is available. On the second leg from Fayette County Airport to Richmond Airport, we'll use pilotage and dead reckoning over to around Moraine Air Park. From there, we'll tune in the Richmond VOR on frequency 110.6 and use it to radio navigate to the Richmond Airport. We'll double-check our position by getting a from reading on the Dayton VOR on frequency 114.5. We'll back up the radio navigation with pilotage and dead reckoning. We'll also check our ground speed to see if our pre-flight computations for flight time and fuel are valid or need to be updated. On the third leg, we'll radio navigate from the Richmond Airport VOR to the Hamilton area, and then tune in the non-directional radio beacon at Claremont County Airport on frequency 245 to guide us to the airport. Again, we'll back up the radio navigation with pilotage and dead reckoning.
On this cross-country plan, you've seen how long trips are nothing more than a series of short trip legs strung together. Even as airliners span the globe, they do it the same way, from point to point. Granted, Their equipment is more sophisticated, but the principle's the same. Later in this volume, we'll actually fly this trip.